So let's jump in. So we finished last time talking about elastic and inelastic collisions. I didn't actually give you any details on those because, there was some, well, actually, it's just because we ran out of time. But today we're going to talk about details. Let's first talk about, oh, by the way, just so you remember, elastic collisions are collisions where the force that caused the collision, like if you have two rubber balls bouncing off of each other, the force is going to be the deformation of the balls and then the force pushing them back outwards. Those are the forces involved in the collision. If the collision force is springy, like a spring between the blocks or just some other conservative force, then we call those collisions elastic. So we're going to talk about elastic collisions first. Right. So if a collision is elastic, not only do we have momentum conservation like we have for all collisions, because we're assuming that there's no external forces involved, we also get an additional equation that will help us solve our problem. We get conservation of kinetic energy. So the reason we get conservation of kinetic energy is because in an elastic collision, there's no changes in the thermal because the only forces involved are conservative, and there's no changes in potential energy because, and this takes a little bit more thinking, but imagine the collision occurs because you have a spring between two blocks that come in and bounce off each other. So initially, that spring has no potential energy, it's just sitting in equilibrium. And after the collision occurs, once everything's far away, the spring will also be sitting in equilibrium. That is to say that there's no permanent change in the potential energy of the system, like the deformation of the rubber balls or whatever. There's no permanent change in the configuration of the system to account for changes in potential energy. Now, in some cases, there will be different types of collisions where you have an increase in kinetic energy before and after collision. And that's because maybe there's some stored potential energy at the beginning before the collision occurs, and that potential energy is converted to kinetic energy. But when we're talking about elastic collisions, we'd say that any potential energy that changes during the collision goes back down to where it started after the collision. So if it's the case that there are no changes in thermal energy or potential energy, and there's no external work done, then all we have is that 0 equals delta KE, which is just to say that the kinetic energy of the system is conserved. So the end result of all of this justification, the end, at least in one dimension, the end result equations that we get for an elastic collision are momentum conservation, which looks something like this. You might have, if you have two objects coming in and bouncing off of each other, you might have m1 v1i plus m2 v2i equals m1 v1f plus m2 v2f. By the way, this is all in one dimension. We're just talking about head-on collisions bouncing off of each other like that. And then we would have, there's a typo in my lecture notes. I need to fix that afterwards. Then you would have the kinetic energy conservation, which is a formula that looks like, well, the initial kinetic energy, 1/2 m1 v1 squared plus 1/2 m2, sorry, that's v1i squared, plus 1/2 m2 v2i squared, that's the initial kinetic energy, is equal to the final kinetic energy, 1/2 m1 v1f squared, plus 1/2 m2 v2f squared. So these are our equations that we would get for a one-dimensional collision that is elastic. So a good example of this might be, come on, scroll please, would be a block moving and hitting another block that was initially at rest. Let's work this out really quick. So before the collision occurs, we have a block of, say, mass m moving with some speed v towards a stationary block of mass m with speed 0. And then there's some elastic collision that occurs, meaning that it's springy. One hits the other. I'm going to draw that by drawing little sparks or whatever. And then after the collision, we have that, and we will find this out later, but we will have that m, the first block, has speed 0, and the second block starts moving away with speed v. Now we need to figure out why this happens. So why is it? Why are the incoming and outgoing speeds the same? So we can justify this just by using the equations above. So we have the momentum conservation equation, and that's because there are no external forces here. It's just the two blocks hitting each other. Yeah, they have equal mass. They have mass. They both have mass m. Momentum conservation gives us that m. I'm just going to use v for the initial velocity. mv plus 0 equals mv1 plus mv2. That's the momentum conservation. And from this equation, we get that v is equal to v1 plus v2. v1, by the way, represents the final speed of the first block, and v2 represents the final speed of the second block. And we're going to show that one of them has to be 0. It's not quite related to it. I mean, in principle, it can be, but you just needed the notion of momentum equation, or of momentum conservation in that case. And then we have kinetic energy conservation, which is that 1/2 mv squared plus 0 equals 1/2 mv1 squared plus 1/2 mv2 squared. And from this equation, we can again cancel out the m's, cancel out the 1/2, and we get that v squared has to equal v1 squared plus v2 squared. So we have two equations that we get from momentum conservation and kinetic energy conservation, and then we can just start slapping them together. So using the first equation, we have that v equals v1 plus v2. By the way, these are not vectors. This is a one-dimensional problem, so we can just use positive and negative numbers. And what that means is you can just square both sides. So that means that v squared is equal to v1 plus v2 squared. But then we can expand that, FOIL it out. We get that this is, but then using this equation, we have that v squared is also equal to v1 squared plus v2 squared. So this has to be equal to v1 squared plus v2 squared. Now, this is not obvious. This is not generally a true statement. Usually there's a middle term. And so we can expand that middle term, or we can FOIL out that binomial term. We would get v1 squared plus 2 v1 v2 plus v2 squared should be equal to v1 squared plus v2 squared. And then we can just cancel off some things. And we're left with 2 v1 v2 equals 0. Which is to say there are two solutions. Which block velocity is the v without the subscript? Yeah, the v without the subscript is the initial velocity. So there are two solutions to this equation. The solutions are the following. There's either v1 equals 0 and v2 equals v, or v1 equals v and v2 equals 0. So those are our two solutions. And by the way, we get that by solving this equation, finding out that one of them is 0, and then plugging that into this equation. So you might have a question, and it's a reasonable question to have. Why is it that there are two solutions? Like, how could it be that if you send a block at another block, that there's two possible outcomes? Like something happens. How do we know which one of these happens? Well, keep in mind that nothing in our setup actually indicated that the first block hits the second block, right? It could have been that this block just passes behind this block or passes over it. In that case, block 1 just stays moving at speed v, and block 2 just stays moving at speed 0. That would be the second case. However, if the first block does hit the second block, then we would have the second case, where the first block's speed changes, becomes 0, and the second block gets all of that momentum. By the way, the case where where one block misses the other, that's also an elastic collision. V1 and V2 are the final speeds, or rather the final velocities of the blocks after the collision. By the way, the situation where one block misses the other block and they just sail on by doing not touching each other, that's also an elastic collision, in the sense that momentum is conserved and kinetic energy is conserved, right? Those are both still true. There's a few other examples that you can find in the Libre text. I outlined one of them in the lecture notes. There's some examples in the Rice University textbook that I also linked to. So go take a look at that. But the basic gist is for one-dimensional elastic collisions, you just set up these two equations and then solve for the unknowns based off of what you know. Now, in principle, it can't be inelastic if there's no collision to begin with. Yeah, there you go. In general, there's a lot of variables. You'd have to be given something. In this case, so you will always need both. Well, not always, but almost always you will need both. In this case, we implicitly were given some of these. For example, we were given that the initial velocity is 0. We were given that the masses were the same, and they just had values m. We were given the initial velocity of block 1. So how many unknowns are there? There's 2 unknown masses. There's 2 unknown masses. There are 2 unknown final speeds. Sorry. The total number of variables are 2 masses, 2 initial speeds, 2 final speeds. So that's 6 variables, right? Now we have 2 equations here. We also know that we are also given the initial speeds. So that's the initial speeds are take care of 2 variables. The fact that the masses are the same take care of another variable. And then we get the final, so then we effectively end up with 5 equations and 6 unknowns. Now, in general, these results would have depended on the mass, but because the masses were the same, and because the system was very simple, that ended up working out on its own anyway. There is a notion that you kind of have to make sure that you have enough information. In this case, we did, but that won't always be the case. For example, had the masses been different, the end results would have depended on the masses, or rather on the ratio of the masses. All right, let's talk about inelastic collisions, which are slightly more complicated. By the way, we are going to go 10 minutes late today. I'm very much trying hard to catch up, but we are currently more than a lecture behind. So going forward, just so you guys know, we have this whole discussion about internal kinetic energy. For the sake of the rest of this class, all of that's going to be thermal energy. So whereas there might actually be internal kinetic energy, we're just going to treat it as thermal energy and it'll be fine. So for a general inelastic collision, some kinetic energy is lost to thermal energy. So the difference between an elastic collision and an inelastic collision is that in an inelastic collision, the internal forces are not necessarily conservative, which means that we cannot say that there's no change in thermal energy. So that is, for inelastic collisions, there generally will be a change in thermal energy. And because the thermal energy generally only ever goes up, like you take away kinetic energy and you convert it to thermal energy, that means that generally the kinetic energy will have, the final kinetic energy will be smaller than the initial kinetic energy. Now, there's a specific type, should be said, we can talk about that afterwards. Where was I? There's a specific type of inelastic collision, which is special, which is called a totally inelastic collision. A totally inelastic collision is kind of as it sounds. It is a collision in which the maximal amount of kinetic energy is lost to thermal energy. Now, you can't lose all of your kinetic energy to thermal energy because momentum is still conserved, which means that the objects still have to be moving. Like if they start out moving, then they have to end up moving, at least in most cases. And so there is a maximum amount of kinetic energy that can be lost, and that's not all of it. It's just some fraction of the kinetic energy that it started with, and that depends on the situation what that fraction is. But there's a different way of understanding this. When that fraction is reached, once the maximum amount of kinetic energy is lost, it turns out that the objects stick together. And this is something that you can prove rigorously. I'm not going to do it. Instead, we're just going to treat a totally inelastic collision as by definition, a collision where the two objects come together and then they end up stuck together and then they keep moving. Like, imagine a gross example, 2 handfuls of mashed potatoes. You throw them at each other, they're going to stick together and then keep going in whichever direction they would end up going. That would be an example of a totally inelastic collision. And the way we can see that it's totally, or the way that we can see that it's inelastic is that, like, the mashed potatoes aren't springy. Like, if you punch mashed potatoes, your fist just goes in and it just like heats up a little bit. And so you could, in principle, and you guys have heard about this, I'm sure, you could, in principle, like, punch your mashed potatoes to cook them. Like, that would work. It would just take a lot. Like, they don't heat up a lot, but they do heat up a little bit every time they take an impact because they're not elastically, because the forces governing the cohesion of the mashed potatoes are, yeah, exactly, hitting a chicken to cook it. The forces governing the cohesion of the mashed potatoes is not elastic. It's like inelastic, I guess. It's like sand. And so when you throw them together, that collision is inelastic, or that collision involves non-conservative forces. And so what we end up with is a very non-conservative force, which means, and the end result being that they stick together. Less extreme examples of this would be when two things bounce off each other, but still lose some energy to kinetic or to thermal energy. And we'll see an example of that in a little bit. By the way, there's a great video, and maybe we should talk, maybe I should send this to you. There's a guy who actually cooked the chicken by slapping it. He developed a machine that slaps like a few hundred times a minute, and he actually did it. It's gross and it becomes mush, but he did it anyway. Maybe I'll send that to you guys. Right. So we can actually express the energy condition in a different way. So for inelastic collisions, we no longer have that the kinetic energy is conserved, right? Because some of it's lost to thermal energy. Sorry. For inelastic collisions, actually, let me add something else here. So when the objects stick together, the implication is that the final velocities are the same. So this means that v1f is equal to v2f. And so this is an equation that we don't have. So for totally elastic collisions, what we end up with is an energy conservation equation that relates the final velocities to the initial velocities. So that's one equation that's one additional equation. Instead of having that energy conservation equation for totally inelastic collisions, we have a different equation, which is just that the final velocities are the same. They're different equations, but you still have the same total number of equations, so you can still solve the same problems. For inelastic collisions that are not totally inelastic, you have a slightly different scenario. So in this case, we have that the energy condition can be written as follows. So we're just going to write down the work energy theorem, but including the change in thermal energy, i.e. 0 equals the change in kinetic energy plus change in thermal energy. And so we can rearrange this to get the kinetic energy after the collision is equal to the kinetic energy before the collision minus the change in thermal energy. Or alternatively, we could rewrite this as the kinetic energy after the collision is some fraction, some percentage of the kinetic energy before the collision. And then the change in thermal energy is just the remaining energy. So these are just two equivalent ways of doing it, i.e. if you know what the final, or what fraction of the initial energy the final energy is, then you can find the change in thermal energy, and vice versa. Like, these are just two different ways of representing the same thing, but sometimes they'll be asked in different ways. So I wanted to present you with both. So in one dimension, we can write our our inelastic collisions and our totally inelastic collision equations. So for inelastic collisions, these are non-totally inelastic. These are not totally inelastic collisions, but they're still inelastic. Our equations look something like this. We would have momentum conservation, as always. This is, by the way, these are one-dimensional results. We'll do two-dimensional after this. We get that M1V1 plus M2V2, V1I, M2V2I equals M1 V1F plus M2 V2F. This never changes. It's always the same thing. Well, not always the same thing, but it's usually the same thing. And then we have our energy condition, which is different from the elastic case. So the energy condition is one of the two above equations. So it's either final kinetic energy 1/2 M1 V1I squared plus 1/2 M2 V2I squared equals, I'm going to run out of space, equals 1/2 M1 V1F squared plus 1/2 M2 V2F squared plus delta E thermal. And sometimes that delta E thermal will be given to you, or maybe you want to find it. Yeah, and I know the subscripts are annoying. Or your energy condition can be given in the form of this final kinetic energy has this much percentage of the initial kinetic energy, which would be 1/2 M1 V1 M1 V1F, no, M1 V1I squared plus 1/2 M2 V2I squared equals, and then it would just be like some fraction, maybe X percentage. So you guys know how to write a percentage in terms of a fraction. 1/2 M1 V1F squared plus 1/2 M2 V2F squared. So those are just two equivalent energy conditions. They're the same type of thing. They both represent energy conservation or conservation of thermal plus kinetic energy. They're just two different ways of writing it. And so these two equations are the equations that you would need to solve a one-dimensional inelastic collision that's not totally inelastic. For totally inelastic collisions, it's very similar. Again, we have momentum conservation, but we no longer have an energy condition. Our energy condition becomes instead that they stick together, which is just it doesn't matter what your equations are. As long as you have the correct number of equations, you'll be able to solve the same type of problems. So here we have a momentum conservation, but then instead we have the totally inelastic condition. Let me just erase all of this. And the totally inelastic condition is that the final speeds are the same, or the final velocities are the same, really. Yeah, I hate you with that copy and paste, sorry. Which is just that V1F equals V2F. At least I'm not lecturing from a PowerPoint, right? Then there would be no writing at all. For elastic collisions, can we still say that kinetic energy? No. So for inelastic collisions, the kinetic energy isn't conserved because the kinetic energy changes, right? The final kinetic energy is different from the initial kinetic energy. But we do know how much it's conserved. It's not conserved by. We know how, we can figure out how much it changes by. So there's a whole bunch of examples, and I would recommend, by the way, I know that I'm not working examples here, but that's because I trust your guys' ability to do algebra. All of the physics of everything that we talked about is in setting up these equations. Once you can recognize when these equations are relevant, once you know what situations these, it's not that it's conserved. That's just what it means for a system to be totally inelastic. It means that they stick together. It's not, nothing's conserved. Why is the energy condition part? So it's an energy condition. Total energy is conserved, but kinetic energy is not conserved. Yeah, the left is, yeah. So right. So my point is the physics in a problem is identifying the what the situation is, or maybe slightly modifying the equations that you know in order to apply them to a new situation. Everything after that is just plugging in the variables that you know, and then doing a whole bunch of algebra. Now, I get that can be challenging, but I can't spend time doing that. I mean, I can in office hours and after lecture, but I'm not going to spend time during lecture doing that because, you guys have all taken calculus. You're all engineering students. I trust your ability to do algebra, so it would just be a waste of most of your time. There are a lot of examples, though, if you do want to look at them, and you should practice. It's useful. But so that's the gist of one-dimensional collisions: elastic, inelastic, totally inelastic. Now we can do the exact same thing in 2 dimensions, and that's what we're going to do now. So 2D collisions. The only difference between 2D collisions and one-dimensional collisions is that 2D collisions are just a lot messier. And I say that with as much mirth as I can because they get really bad. So let me give an example before we actually start talking about it. So let's say that you have a ball, make it red, and it's moving with some initial speed or initial velocity v, right? And let's say that it's going to go hit a stationary ball, speed velocity 0. Let's say that this ball has mass m1 and this ball has mass m2, right? So there's a whole bunch of things that could happen. They could hit direct, or one could hit dead on to the other, in which case it would just be a one-dimensional collision, or they could like bounce off each other in like at an off angle. A whole bunch of things can happen. So clearly you need to know a lot more about the system to even be able to solve it. By the way, the coordinate system that we're going to use for this problem is the standard one where we have x in the horizontal direction and y in the vertical direction. So in the before case, we have that the initial total momentum is m1 v. And in the vertical direction, the initial total momentum is 0 because the momentum of the, there is no momentum for the second ball and the first ball is only moving in the x direction. So we're going to need that. Then there's a collision. And maybe they hit head on, maybe they don't. The point is that they hit somehow. And, you know, sparks happen, a collision happens, they bounce off each other, whatever. And then we would have after the collision. Something happens after the collision, they fly off in whichever direction. And so maybe you have one of them goes off, one of them goes off, say, this way, speed or with velocity v2. And maybe the other one goes off, say, this way, maybe with velocity v1. And so we need some system to measure these, because all I've given is speeds. I haven't given actual vectors. So what we might do is we might measure angle relative to the horizontal axis, call that theta2, call this theta1, and then we can characterize the vectors. So the vector v2 would be the magnitude of v2 would just be the speed v2 times cosine of theta2 in the I hat direction plus v2 sine theta2 in the j hat direction, and then we could do the same thing for v1. Just as a caveat here, theta1 is negative in this case, and it's negative because we typically measure angles above the x-axis. It's a convention; it doesn't have to be, but that's the way that we do it. And so then the momentum afterwards would be, well, what's the x component of the momentum of v1? Well, that would just be m1 v1 cosine of theta1. So that's the x component of the momentum. And then the x component of v2 would be m2 v2 cosine of theta2. Similarly, the momentum in the y direction would be m1 v1 sine of theta1. In this case, remember that theta1 is negative, so this whole thing is negative, which accounts for the fact that the velocity vector points down and to the right. Plus m2 v2 sine of theta2. Okay, so now our momentum conservation equation becomes the following. Or now, remember, momentum is a vector. So if we conserve a vector, that means that all the components of that vector are the same. And so we set the x components equal, we set the y components equal, and so we have the following equations. We have, in the x direction, the initial momentum was m1v, and that should be equal to m1 v1 cosine of theta plus m2 v2 sine of theta. Sorry, also that's cosine of theta 1. This is cosine of theta 2. And then in the y direction, we have that 0 because that was the initial momentum in the y direction, equal to m1 v1 sine of theta 1 plus m2 v2 sine of theta 2. So you would need these. So these are your two momentum conservation equations. And there's two of them because there's two directions here. Now, just as a point of reference, there's 7 variables here. and only 2 equations. So in principle, you need to learn about 5 more equations or 5 more data points in order to even be able to solve this equation, which seems like a lot. But in general, solving these equations are the same conceptually as solving them in 1 dimension. All you do is you write down all of the equations that indicate information that you know, like m1 is equal to this. That's technically an equation. V is equal to that. Theta 1 is equal to this. Those are all equations, or maybe you know that m1 equals m2. That's also an equation. You write down all your equations, and then you slap together the algebra, and then you just do it. You just solve for your unknowns. In this case, you would need to know 5 unknowns, which is a lot, but there are other ways that we can provide information. So before we continue with how that information is typically provided, I want to back up and abstract a little bit. So what happens? What if, so here we need five more pieces of data, right, to solve any sort of problem here. So what if both balls are initially moving in arbitrary directions? So one of them is not just moving in the x direction, and the other one is not stationary. Well, we can actually translate an arbitrary collision, 2 things coming in at some angle, whatever velocities, into this problem above, where we just have one ball moving in the x direction and the other one being stationary. So the way that we do this is step 1, we change reference frames. Remember that whole reference frame business? I promised it would be important. We change reference frames to the rest frame of one of the balls. And then step 2 is we rotate or choose a rotated coordinate system. And this rotated coordinate system is in the reference frame of one of the balls. Choose a rotated coordinate system so that the other ball moves along the x direction. So pictorially, let's say that you have ball A, ball B. So ball A is here, ball B is here. Maybe this ball's coming in this way, this ball's coming in this way, right? And so maybe we start with some coordinate system like this, x, y. Well, the first step that we do is we would work in the reference frame of ball B, say. So remember, to get the reference frame velocity of ball A relative to ball B, so that's what the rest frame of ball B means, by the way, when you are working relative to that ball. So we want to know the velocity of A relative to ball B. You can do that by this notion of relative velocity. And so what it ends up being is the velocity of A relative to the velocity, or relative to B, is the velocity of A in this lab frame, like the stationary frame, minus the velocity of B. So what we end up with is velocity of, I'm actually going to copy and paste again because I know you guys love that. Oh boy. There we go. Oh, why does it keep going up to the top? Paste. I'm just copying and pasting so it looks consistent. So to do the subtraction, we have to reverse the velocity of B and attach it to the velocity of A. And then we do our standard vector addition. So the velocity of A relative to B, so this is A rel B, we are now in the rest frame of B, because now the velocity of B in this frame is 0. And then we do our second step. This is actually perhaps a bad example because the second step is relatively trivial. But we want a slightly rotated coordinate frame so that it aligns with our x-axis. So we just rotate our coordinate system. We just choose a new set of coordinates. And now we see that A, in this new coordinate system, this moving reference frame with a rotated coordinate system, is exactly the same situation that we had before. One ball comes in, the other ball stationary, the first ball is along the x-axis, and so on. And so we still only need 7 variables and 2 equations. Or sorry, we still only need to solve for 7 variables. Which means that we need to be given 5 pieces of data in the reference frame of the ball. I know it's only, but like there is something to be said that it's better than 10. It would have been 10 otherwise. Also, just as a point of something to add here, sometimes it's also helpful to work in the rest frame of the center of mass, right? Work in the center of mass frame so that the total momentum is 0. That can also sometimes be helpful. There are situations where that will be useful, and so I will leave it up to your creativity to figure out when that happens. Maybe there will be a homework problem that involves that too. Right, so how do we actually figure out what those extra variables are? So far, we've only given momentum conservation, which holds for generally any collision. But we also need to talk about energy conditions, right? What is it, inelastic? Is it elastic? And so on. So let's talk about this. So the additional information is provided in a few different ways. So one way that it'll be provided will be by an energy condition. So that will be something like, maybe the problem tells you this is a totally inelastic collision. This is an elastic collision. This is an inelastic collision, and 30% of the energy is lost. Those are energy conditions. Yeah, so we're just adding negative b rather than subtracting b. That's all we're doing. So this gives us generally one equation. Well, actually, it gives us between one or two equations. Yeah, one or two equations. By the way, it can give you two equations if you know that the final velocities are the same. For totally inelastic collisions, it's two equations because you have both components of the velocities are equal to each other. All right, this too occurs when totally inelastic. So for collisions, at least for what we're talking about, momentum is conserved so long as there are no external forces. So for collisions that we're talking about, we generally ignore the external forces, in which case momentum is conserved. Other additional information might be given in the form of experimental data. Experimental data. These would be things like M1 equals or V1I equals. These are just things like initial values or things that somebody tells you, just numbers. Those are technically equations and they count. And then the third might be geometric data. These are things like, oh, they ricochet off each other at a 90-degree angle or something like that. Theta equals distances and so on. This is just any data that's not like a direct measurement, but more in the sense of like given like a diagram, you could learn data about the problem from looking at that diagram. So that's kind of like the third type of way that you'll be provided information. And usually it'll be a combination of these three. You'll almost always be given an energy condition. You'll almost always be given some experimental data, and sometimes you'll be given geometric data. And then you can combine them in whichever way, and hopefully you have enough pieces of information to solve the problem. Now, sometimes you won't actually need that many equations. Like if for example, something cancels out nicely because of one of the pieces of data you were given, then maybe you actually only need 6 pieces of data, not 7. But that can happen, just warning you. Right, so just as a quick aside, and I noted this in the lecture notes, but I'm just going to briefly talk about it, is that it is possible for collisions to be what you might call super elastic, which would just be that the final kinetic energy can, in particular, be greater than the initial kinetic energy. I briefly touched on this earlier when I said that if there's some initial stored potential energy, imagine that there's like a spring that's like cocked, like it's already really compressed, and then you launch that spring at another object. Well, the spring's going to release its energy, or it's going to release its stored potential energy, and it's going to convert that into kinetic energy. So the initial kinetic energy of the system might be lower than the final kinetic energy of the system because the potential energy went down. That's possible. It's pretty rare, but it could come up. So once you have all of these pieces of data and you have your momentum conservation equations, then it's just algebra. And I know the algebra is messy and the algebra is awful and terrible, but it is in principle just algebra. And if your algebra is weak, go practice. Otherwise, go practice setting these up, and you will get lots of practice, I promise. Right. So let me go over a nifty piece of data, or a nifty calculation. It's a little bit complicated, that I think you guys should take a look at. So, yeah, this homework problem, or this homework set is generally going to be challenging. Algebraic, like conceptually, it might not be that difficult, but it will be hard. I mean, they're always hard. What can I say? So let's talk about elastic 2D collisions. And by the way, just because they're hard, that doesn't mean you should go and do, like look up answers online. Like they might be there, but don't use them because I will catch you. I've reported so many people for this particular homework because this homework's hard. So just please don't do that. Just struggle with it. And it's okay if you don't do perfect on it. Like, remember, only one problem is graded for correctness. So, the odds of the one very hard problem being the one graded for correctness, relatively low. Anyway. So we can actually learn information. We can actually learn information about an elastic collision without using any coordinates, without transforming to reference frames or whatever. We can actually just solve a problem by being careful and being clever with our algebra. So imagine that we're in this situation above, right? You have one ball hitting another ball, and the first ball is moving in the x direction. The second ball is stationary. So in that case, we have that the kinetic energy, the initial kinetic energy of the system. So actually, let me write something really quick. So assume above situation. In this case, V2i equals 0, V1i equals V1i in the I hat direction. Okay. So in that case, we can actually write the kinetic energy in terms of its potential energy. Sorry, not potential energy, in terms of its momentum. Remember that we had a formula for kinetic energy in terms of momentum. It was something like p squared divided by 2m. That still holds here, but because we're talking about vectors, p squared means the dot product of p with itself. And then we divide by twice the mass of the ball that has that momentum. And so here, by the way, we're saying that p without any subscripts is the initial momentum of m1. So that's the initial kinetic energy because m2 doesn't have any momentum. And then I'm just going to define some variable names for you. So p1 will be the final momentum of m1, and p2 will be the final momentum of m2. Just that so that we have our labels. So then the final kinetic energy is something like p1 dotted into p1 over 2m1 plus p2 dotted into p2 over 2m2. This is the final kinetic energy of the first ball. This is the final kinetic energy of the second ball. So now we can use momentum conservation. So we don't have to even work in components here. We can just use momentum conservation to write that p is equal to p1 plus p2 as a vector sum. That has to be true, right? And then we can use this fact to rewrite our initial kinetic energy by substituting in p equals p1 plus p2. So this is 1 over 2m1 times p1 plus p2 dotted into p1 plus p2. And then we can distribute and FOIL. So just do all the distribution, do all the foiling, and so on. Do all the dot products. I'm just going to shortcut it a little bit. We get 1 over 2 m1 p1 dot p1 plus 1 over m1 p1 dot p2 plus 1 over 2 m1 p2 dot p2. Now we can use energy conservation. This is an elastic collision. So we have the final kinetic energy is equal to the initial kinetic energy. And so we can relate the initial kinetic energy to the final kinetic energy. And that's what we're going to do. So I'm going to copy and paste. I know you guys hate this, but you don't learn anything from me actually spending time to write these down. This should be equal to p1 dot p1 over 2m1 plus p2 dot p2 over 2m2. So all I've done is I've expanded out the initial kinetic energy by using momentum conservation, plugging that in there, and then setting kinetic initial to final kinetic energy. I know you missed numbers. Sorry. Welcome to university. This is physics. Okay. So now we can just start manipulating this expression. So right away, these two terms are the same. So let's cancel them out. P1 dot P1 divided by 2m2 or 2m1, and the same thing on the left-hand side. And then I'm going to take this term, move it over to the right, multiply both sides by m1, and then I'm going to factor. So the end result of all of this is that we get that P1 dotted into P2, this is equal to 1/2 m1 divided by m2 minus 1 times P2 dot P2. And now we have the trick. So remember, P1 dot P2, by definition, like this is how we define the dot product. This is equal to the product of the magnitudes, so P1 times P2, times the cosine of the angle between them. Now let's scroll up and look at what the angle between them is. So the angle between them should be θ2 minus θ1, right? So if θ1 were positive, it would be like this angle, so θ2 minus θ1. But because θ is negative, we get a slightly larger angle. But nonetheless, the angle between them is θ2 minus θ1. And by the way, we could have written θ1 minus θ2. It's the same way. It's the same thing because cosine is symmetric. Now, we know what the magnitudes of these are. We have variables v1, v2, and v. So P1, the magnitude of P1 is just m1 v1. The magnitude of P2 is just m2 v2. This is times cosine of θ2 minus θ1. Similarly, P2 dot P2 is just m2 v2 squared. All right. Now, we're almost done. We know that this is equal to a coefficient times that. So we have that m1, m2, v1, v2 cosine of θ2 minus θ1. Wow, this is really messy. Equals 1/2 m1 over m2 minus 1 m2 squared v2 squared. All right. Do a whole bunch of algebra. We're just going to solve for cosine of θ2 minus θ1. And we're left with cosine of θ2 minus θ1 equals 1/2 1 minus m2 over m1 times v2 divided by v1. Or evaluating. So you're not expected to do this. This is just a nifty result. Evaluating, we get that θ2 minus θ1, which is, by the way, the relative angle between these two angles, or between these two vectors. This is the inverse cosine of 1/2 1 minus m2 over m1 v2 over v1. All right, it's a whole bunch of work, but we got pretty far. And so what does this tell us? This tells us that the only thing that affects the output angles is a ratio, or it is the ratio of the masses and the ratio of the final speeds. Those are the only things that affect the angle, which is kind of surprising. Like you might think that like another thing that affects the angle is like how glancing is the blow, but that's all captured by this information. For example, if it were the case that M2 was, what would be a better example? If it were the case that M2 is equal to M1, i.e. if M2 divided by M1 is equal to 1, well then the inverse cosine of 0 is 90 degrees, which means that if you have two masses that are equal to each other and you fire one at the other, they will always go off at a 90-degree angle. We won't necessarily know where that 90-degree angle is, but the relative angle will always be 90 degrees. So you can learn a lot just by looking at like, from this particular example or this particular calculation, just by looking at limiting cases. Like what if M1 is really, really big compared to M2? Or what if M2 is really, really big compared to M1? You can figure out what the relative angle is without having to do any sort of like component calculation. So it's relatively powerful. This is, by the way, what's known as the scattering angle, and it's used all over the place in higher level physics. Like this is the kind of calculation that they have to do at like the Large Hadron Collider. All right. So we got almost as far as I would have liked, which is fine. Like, we went way over, and I'm very glad that we got as far as we did. I'm going to stop the lecture here. I know you're going to need time